Let us now try to understand the working of a bipolar junction transistor. In this lecture, I will illustrate the working of PNP transistor. I hope after understanding the basic working principle of a PNP transistor, you will be able to discuss the working of the NPN transistor. So let us first see the structure of a PNP transistor. Here in this diagram you can see there are three different regions: emitter, base and collector. As I am discussing the working of a PNP transistor, so it is consisted of P region, N region and another P region. Okay, and there are three different terminals as I've already told you, that is emitter E, base B and collector C. Now let us see what is within this P material, P-type extrinsic material. As you know, a P-type extrinsic material has a plenty of holes and a few number of electrons. That is, within this P-type material, holes are the majority carriers and electrons are the minority carriers. And within this N region, electrons are the majority carriers and holes are the minority carriers. That is, the number of the electrons within the base region, within this N-type base region, is much larger than the number of the holes. And here in the collector, as it is P-type, so here also the number of the holes is quite larger. So holes are the majority carriers and electrons are the minority carriers. Okay, so accordingly we have to draw the symbols for the holes and the electrons. As you know, electron is a negatively charged entity, negative charge carrier it is, and hole is a positive charge carrier. So we have to draw a number of positive charges here and few electrons. And here the case is opposite. Here we have to draw a number of electrons and few holes. And here also likewise we have drawn, in case of the P-type emitter region, we have to draw, it is comparatively wider region. In comparison to the emitter region, this base region is wider and this collector region is wider, and the base region is the narrowest region. That is, it is the thinnest region. I have already told you previously. Here in the P-type collector region, you have to again draw a number of positive charges and few electrons. Okay, so this is the scenario. That is, within this P-type material there are a huge number of holes, and here the number of holes is quite small, and here the number of the holes is quite large and the number of the electrons is quite small. So under this scenario, that is under this condition, yet no depletion region has formed. Now due to the concentration gradient, as you know, there is a very important term which we called concentration gradient. What is it? It is actually the difference of concentration. That is, the number of holes here is quite large and here the number of holes is quite small. So due to this difference in the number of the holes between these two regions, holes will start to flow from this side to this side, and electrons will start to flow from this side to this side, because here the number of electrons is quite large and the number of electrons here is quite small. So always there will be a charge flow from the higher concentration to the lower concentration. So due to this flow of electrons and holes, there will be a diffusion current, and one current will be diffusion hole current. We can write it IHD, diffusion hole current, and here we can write IED, diffusion electron current. Now after reaching here, these holes will be the excess carriers here, and after reaching here, electrons will be the excess carriers here. Here, the holes will start to recombine with the electrons. But here, as I already told you, that the doping concentration of the base region is quite small. It is intentionally made small because if it would be quite large, that is, if the doping concentration would be large, then more number of holes will recombine. Recombination means that is when a positively charged hole recombine, that is recombine with electron, this whole system will get neutralized, will be lost, the charge will be lost. So a number of electrons and holes are recombining with each other, and due to this there will be a recombination current, and this will give rise to a base current here. And finally, after recombination, these holes, these carriers will travel into the collector region. As the name suggests, collector means the electrons and holes will be collected there, and this region is intentionally made larger. This is about the diffusion current. What about the drift current? The holes are traveling or transiting from the emitter into the base region, and the electrons are transiting from the base to the emitter region. There will be excess carriers, and between these carriers there will be an electric field, that is a force of attraction, or there will be a depletion region, we can say, that is here, as in the p side region there will be negatively charged ions, these are the immobile ions, and here will be positively charged immobile ions. Okay, and there will be an electric field between the positive and negative charges, and this electric field will work further as a force and will make more number of charges to move across the junction. And across this junction too, these two junctions J1 and J2 are the PN junctions. This is also called the emitter base junction, JEB, and J2 junction is also called the JBC, that is the base collector junction. So here also, as you have seen in case of a PN junction diode, across the PN junction there is a depletion region. So same thing will happen here. So there is a depletion region. In the side of the p-type material there will be negatively charged immobile ions. These are not electrons, these are the immobile ions accumulating here, getting stored here. And here in the n-type side there will be positively charged immobile ions will be accumulated here. It is across the either side of the junctions. Now there will be electric fields across the positive and the negative charges, and the electric fields, this generated electric field is actually responsible for the drift movement. So finally we are getting currents even when it is a no bias condition, that is still we have not applied any voltage across the terminals, right? Now, to understand the working of a PNP transistor properly, the emitter base junction is made forward biased. As you can see, it is a p-type material and it is connected with the positive terminal of the voltage source VEE through a resistor RE. So this resistor is optional. Now this junction, due to this connection, this junction, that is the emitter base junction, which is a PN junction, is made forward biased, and this collector base junction, that is the JBC, is made reverse biased with this voltage VCC, As you can see, p-type semiconductor is being connected with the negative terminal of the voltage source VCC of the resistor RC. So obviously this junction is reverse biased. Now the emitter base circuit, that is this circuit, being forward biased helps the movement of the holes, as here the number of the holes is quite large, as I already told you, is quite larger than the number of the electrons. So the movement of the electrons will become easy in the p-type material to the n-type material. Towards the n-type material, that is holes will move towards this junction between the emitter and base. On the other hand, the collector base junction, that is this junction JBC, being reverse biased, does not allow the holes in p-type material and the electrons in the n-type material to move towards the collector base junction. As you know, in case of the PN junction diode, you have seen that is under the reverse bias condition, the current flow is very much restricted. That is, a minimum leakage current flows across the junction, okay, which is called the reverse saturation current. So in this case also, due to the reverse bias of the junction, this depletion layer will become wider, and this spread will be much more inside this base region because it is lightly doped. So it is quite easier for the depletion region to spread into the n-type material than into the p-type material, because the p-type material is medium doped or moderately doped. So it will extend, as you can see here, and this width become wider. And on the other hand, if you draw the energy band diagram, then the barrier height will become larger. That I will illustrate later. Okay. Now here you can see the main current is flowing across this junction because it is forward biased, and here there is a minimum flow of the current. The holes in the emitter and the electrons in the base are repelled by the positive and negative terminals of the voltage source, that is this voltage source, because it is positive terminal is being connected with p-type. So holes cannot go to this side, and electron, as it is being grounded or it is being connected with the negative terminal here, so it is not able to go this side. So holes are repelled by this positive terminal of the voltage source, and electrons are being repelled by this negative terminal of the voltage source. Now, on reaching the emitter base junction, that is upon reaching, that is holes will start to reach this junction and electron will start to reach this junction, right? So on reaching this emitter base junction, a small fraction of, that is 5% of the total number of holes, that is if there are, for example, if there are 100 holes, then 5 holes, 5% of the total number of the holes will recombine with the electrons in the base region, right? As it is lightly doped region, so the number of the electrons is also small, and it is medium doped region, so here the number of the holes is comparatively larger than the number of the electrons here. So due to this, only 5% of the holes will recombine with the number of the electrons here in the base region, and due to this recombination process, there will be the holes and electron system will get neutralized. Now as the base region, as you can say, I already told you, that is the width of the base region is quite thin, and the collector is given a high negative potential. As you can see, this negative potential is given here, and due to this, the holes will rush, that is they will be attracted by this negative terminal of the voltage source, will rush towards the collector, as already 5% of the holes are being recombined here, that is 5% of the holes are lost here. Okay, so remaining, that is 100 minus 5, that is 95% of the remaining holes will move towards this negative terminal of the voltage source VCC. And so 95% of the holes will be collected by the collector. So the name is justified, right? So finally what we can write, that is, as the name is emitter, that is the charges are emitting, they are going into the base region, recombining there, some few percentage get lost, approximately 95% is being collected in the collector region. So if we write the equation, then finally here also we can write this current, that is, it is the emitter current. As you know, in the direction of the hole, the current flow, that is, if a hole is flowing from this in this direction, then the whole current will flow in this direction, or the current will flow in this direction. Or if the electron is flowing in this direction, then the current will flow in the opposite direction. So here also, by considering the flow of the holes from P to N, the current is flowing from P to N, that is, the current is inward. The symbolic representation also you have seen, that is, we have drawn the emitter current inward, right? I hope you remember. And here the base current is outward. It is actually the recombination current, and it is the collector current which is also outward. So finally what we can write, this is the main current, emitter current. So finally we can write emitter current equal to IB plus IC. That is, the total current supplied, IE, is equal to the sum of these two currents, IB and IC. You have to remember this equation. This is a very simple equation, but this is a very important equation you have to remember. Okay, thank you.